In this unit, we're going to be looking at kind of a overarching view of chemical reactions, why they happen, how we can get them to happen, and kind of end it on looking at some of the types of chemical reactions that you're going to see, and look more in depth on how they occur and what precisely is involved with bonds breaking and bonds forming. So a lot of this in the beginning is going to be review from general chemistry, but it's going to kind of frame the remainder of the unit. So that's why I'm gonna review it. So first of all, why do chemical reactions occur? Um, think of this like rolling a ball down a hill. So you have, let's imagine we have this hill here, and we put a ball at the top, and we'll look at this as a measure of potential energy. Now, if we push that ball, it goes down the hill, and eventually it reaches an energetic minimum. And that's kind of the governing force behind a chemical reaction is much like that ball, um, molecules, compounds want to have this energetic minimum. That's where it's the most stable. And chemical reactions are pretty much governed by the second law of thermodynamics, which basically, if you remember that from GChem, says the entropy of the universe is always increasing. And kind of along with that, for any spontaneous reaction to occur, spontaneous means it happens on its own under the conditions that we're using. So for any spontaneous reaction to occur, the entropy of the universe is increasing. Now, one thing I do want to note is that a lot of times it's quote unquote hard or difficult to deal with the universe. So a lot of times we just limit that to just looking at the system. And so the formula that you used in general chemistry to determine if a reaction was spontaneous or not, or non-spontaneous, was looking at Gibbs free energy, which is delta G equals delta H of the system. H was dealing with enthalpy minus T delta S of the system. And S is entropy. And if delta G was negative, that meant the reaction was spontaneous, or what we called exergonic. If delta G was positive, then that reaction was non-spontaneous, what we called endergonic. And just because we determine something to be non-spontaneous doesn't mean it doesn't happen. It just means we have to tweak the reaction conditions a little bit. So let's review each of those terms individually. So enthalpy, or what was specified as delta H. Again, let's take this from the standpoint of we want a spontaneous reaction. So we want delta G to be negative in order to be spontaneous. Now, what does that mean delta H should be? Well, we would want delta H to be negative in order to favor the reaction occurring. And the term we gave to a negative delta H was exothermic. There is a release of energy. And so delta H is just simply the enthalpy of the reaction, or also known as heat of reaction. And again, that's something that's covered in general chemistry. We're just measuring pretty much the change in kinetic energy. What was the energy change between the products compared to the reactants? And one of the major ways that we measure or quantify this is looking at bond formation and breaking. What's the difference in energy between those two processes? Now, it is important to remember that bond formation is an exothermic process. It releases energy to go from something less stable to more stable. For example, let's look at a little review of the fluorine-fluorine bond. And if we set up a molecular orbital diagram, we have our uh, one fluorine atomic orbital and another fluorine atomic orbital, and each of them are going to give an electron. So we combine those to make molecular orbitals. We have a bonding molecular orbital, an anti-bonding molecular orbital. So the bonding molecular orbital is lower in energy than the atomic molecular orbitals. So energy has to be released in order to form that bond. That's why it's an exothermic process. Now, the reverse process or bond breaking requires energy. That's an endothermic process. You have to put energy into the system in order to get a bond to break. And in general chemistry, you learn this as this is called bond dissociation enthalpy, or BDE is the acronym for that. And that's stuff you can look up. You just look up in the data, the tables are usually reported under standard conditions. You might remember the little circle there just means standard conditions. And so if you look at an example of this, let's take a look at this reaction here. So we're going to take methane and react it with bromine. And what will happen is one of those hydrogens on methane will get replaced with a bromine, and then that hydrogen that got replaced will go to the other bromine atom. Now, in order to calculate the delta H for this reaction, the enthalpy, we need to know what bonds were broken and what bonds were formed. So let's look at our reactants. The first bond that we see that was broken was a carbon-hydrogen bond. So bonds broken, we have a carbon-hydrogen. And then also on the reactant side, there was a bromine-bromine bond that got broken. Now let's take a look at what bonds were formed. So on this product, a carbon-bromine bond was formed. And on this product, a hydrogen-bromine bond was formed. So what we're going to do is look up the dissociation enthalpies um, um, for this. So we have for carbon hydrogen, that's 435 kilojoules per mole. For bromine, that's 193 kilojoules per mole. Bonds forming, we're going to use the opposite sign here. For carbon bromine and for hydrogen bromine, again, using an opposite sign. Because energetically, they are opposite processes. And all we're going to do is add up all these numbers. We add it all up, and that comes out to negative 33 kilojoules per mole, which again, that means it's an exothermic reaction. It releases energy. And if we're going to diagram that, comparing the energy or enthalpy, our reactants are somewhere up here. Our products are somewhere down here. And this distance, the difference between reactants and products, the enthalpies, is delta H. Now, what this diagram tells us is what the beginning and the end is. It doesn't tell us how it got there. Was there a large activation energy? Was there a small activation energy? Or maybe there were multiple steps to get there. We don't know. We can't really tell that by calculating delta H. All we know is that the energy of the products is less than that the reactants. That's how we know it's exothermic. What does an endothermic look like? Well, an endothermic, the energy of the products is greater than the energy of the reactants. So let's look at the next term in our delta G formula, and that's entropy. So if I want, again, for a spontaneous reaction to occur, I need delta G to be negative. What sign should delta S be to be kind of like the optimal condition for delta G to be negative? Well, since this last term here, we're subtracting that T delta S, we want delta S to be as positive as possible to favor the reaction occurring. Because that would make this term as big as possible. And so if we're subtracting a big number, we're making it even more, that whole term more negative. And so delta S is the change in entropy, which is just kind of a measure of disorder or chaos. Now, there's a number of ways that you can kind of judge what the sign of the entropy should be. Not necessarily, you'd have to kind of calculate if you wanted the exact numbers, but you can always predict what the sign will be. Number one is you look at the number of microstates. And this is just the number of ways you can organize a system. So let's kind of compare solid to liquid to gas. So the three states of matter. In GChem, you know that solids have very low entropy because things are highly organized. And there's very few ways you can organize that solid. A liquid starts to increase the entropy, so it's a little bit higher in entropy, even though the molecules are still close together, they can move around. So that you can organize those molecules around in more ways than a solid. And something that's gaseous, the molecules are far apart and they're free to move in whatever direction they so choose. That has the highest amount of entropy. Now, the second way you can look at the sign of entropy, especially in a reaction, is looking at the number of molecules. And what I mean by this is let's look at the number of molecules a reaction forms, or um, does the number increase or does the number decrease? So let's take this compound here, A bonded to B, and we do some sort of reaction, and now we have two separate molecules. Here we went from 1 to 2, increasing the number of molecules increases the entropy. The opposite would be true if I went the other direction. If I took 2 molecules and made it 1, then that decreases the entropy. And finally, the third thing where we can judge the sign of entropy is by looking at freedom of movement. And what I mean by this, let's compare, for example, like cyclohexane compared to regular hexane. Cyclohexane, actually, I won't use a reaction, I'll just say versus. is very highly constrained. And so there, what I mean by constrained is we can't do a lot of rotation. There's not a lot of freedom of movement. But if you open that ring up, then you got all of these individual single bonds that you can rotate around. So there's more freedom to rotate. And so this system would have a higher entropy than something constrained to a ring. So let's just kind of look at a few examples of this. And we're going to predict the sign. We're not going to actually, formalize the numbers. We're just going to predict what the sign should be for these reactions. So if we look at A, we're starting with two molecules and we're going to one. That is more ordered, and so you would expect delta S to be negative here. Entropy will go down. Now let's skip over to C just to compare it because it's the same reaction but in reverse, where we're going from one molecule to two. And so an increase in the number of molecules is going to result in an increase in entropy. Now with B, we have one molecule on the left, one on the right. So we're not in, we can't judge it, the entropy based off of that. But we're going from something that has a lot of some single bonds in there. So there's a lot of rotation to something that's more constrained. So this has more entropy. This has less entropy. That results in a decrease overall of the entropy. Now, if we look at D, we're starting with one molecule, ending with two. That's an increase in entropy. With E, there are two reactants there combining to form one product. So that's a decrease in entropy. And in F, very similar to B, there's only one reactant, one product. But what's the difference between them? Well, F is in a ring, or I'm sorry, the reactant for F is in a ring. That's highly constrained, not a lot of freedom to move around. And then throughout this reaction, the ring opens up, and now there's a lot more freedom for all of those single bonds to rotate completely. So that is an increase in entropy. Now, finally, let's put all this together because we talked about entropy, we talked about enthalpy. We put all of those together to look at whether a reaction is spontaneous or not. Again, ideally, we want, if for a reaction to be spontaneous, delta G has to be negative. The ideal conditions for that is for delta H to be negative and delta S to be positive. So we want an exothermic reaction and we want an increase in entropy. So let's look at the conditions for which delta G will always be spontaneous. Well, as we said, an exothermic reaction that increases entropy is always spontaneous. On the flip side of that, an endothermic reaction that decreases entropy will always be non-spontaneous. So those are kind of like our two extremes. It doesn't matter what temperature is for both of those two statements, Temperature could be high, could be low. The result will always be either spontaneous or non-spontaneous. So what about kind of everything in between? A mix of the above conditions depends on T to make the reaction spontaneous or non-spontaneous. So what I mean by that, for example, is um, an exothermic reaction, right? Delta H is negative with a negative delta S. So by changing temperature, that can affect the outcome of whether delta G is negative or positive, or vice versa. An endothermic reaction where delta H is positive with a positive delta S. So the magnitude of the temperature will affect the overall equation to make delta G either negative or positive.